Would you guys mind if I got started early? I've got a lot of slides and a lot to get through. Yeah, you good? All right. Can you guys read this? Is that clear? I was messing with this, the font and the gradient, and it's like I had to change the color of the font as I went down the slide. It's a terrible slide. Right there? I have no idea what that is. I'll give you guys a couple, like a minute to read through. Do you want me to read it to you? Can you guys read the observations? You ready? Okay. If you guys have a guess, raise your hand. No, the baud rate is both set on both of them correctly. I double checked that. This is softball. It's the easy one. No, but that's a good question. No, just single cable. That's a good one. I've had that problem before. No, it's more simple than that. Nope, that's not it. No. That's it. That's the one. It's the ground. And I can't tell you, this is one of the first debugging experiments that I had, and I was struggling with this one, and it was a good lesson in grounds and sharing grounds. So my motivation for doing this presentation is, well, first of all, welcome and thank you for joining the presentation. There are no silver bullets with hardware debugging. It's difficult. I'm just going to be flat out and I'm going to say it. But I'm going to give you guys some tools and some techniques that should help you collate, locate things, and test different things. And I hope that these tools will help you guys. I was the last year that I was going through a life change. I was leaving a startup in California, coming back to Oregon. I had a couple months where I was searching for a new job, and I was sitting there and I was thinking, because when you're interviewing, you have to tell your strengths, right, and your weaknesses. And one of the things that I really was thinking about was like, I was always put on the projects to fix them. And I always joked that I was put next to the closet, I was close to the mop because I was cleaning up everybody else's mess. So I decided that I'd like to share this because I've seen it done wrong so many times, and I hope that this will help everybody out. About me. Is that, sorry. Right. Thank you. Amateur. Amateur hour over here. Went to school in CU. I've had 25 years of embedded electrical engineering experience. I've had sectors in experience in sectors ranging from military, vision systems, big iron networking, and I also worked for commercial products making VR headsets for startups. 12 years consulting. I've been a part of 4 startups, and I have a crowd supply campaign that was currently in pre-launch. TLDR, I've made lots of mistakes. I've fixed a lot of other people's mistakes, and I want to share what I've learned with all of you. So one of the things that I've seen, and this has been surprising with a lot of people that were senior, is that I feel like they do hardware debugging wrong. And most of the time, people default to something called shotgunning, like Elmer Fudd here. They just try stuff and they waste time without having really any reasons. And you can go down that route and you can get lucky, but if you're working for a company, time is money, and you really want to solve your problems quickly. They've also been seen people blaming others, and I've been guilty of this too, but we're all on the same team, so don't be a dick. And then crazy storytelling. The last one just blew my mind when someone was saying, like, well, that's our problem. We have outer space particles coming down and changing our memory bits. That's the only way to explain this. And it's usually not something like that unless you're doing satellites, I guess. So before we dive into things, I want to explain that there are different scenarios for hardware debugging, and the way that you approach these will be different because of what you have available to you. If you have your own design, you have access to all the design files, you're intimately familiar, and you have the power to change it. Sometimes when you're working on a device, you don't have the power to change something if you're buying it from somebody else and you're doing mass production. And then it can go further down to where you're doing remote debugging. If you guys are technically savvy, when you get a phone call from your parents and they're like, my TV's not working, or my computer's not working, or you're just always kind of like the tech support person. That exchange is a little bit different when you're working with somebody that's not technical. You have to ask them questions or try different things, and you might need to explain things to them, and they may not know what you're talking about. And then broken equipment. You buy a 3D printer. It's not working. It's printing garbage or the motor stopped working. Sometimes if you bought it from Alibaba, you're not going to get a data sheet. You're not going to get any technical support. You have to figure out how to clean it up or figure out how to fix it yourself. So my philosophy on debugging is it's always evidence-based. You should have observation or evidence lead you to where you're debugging. Don't just randomly try stuff or holistically just feel like, oh, I should try this. Your test should be prove causal relationships. You should conquer and divide. Every time that you do something, it should take you away from looking at power supplies or something else, or other theories that others may be throwing at you, like your manager saying, I want you to try this, and you're like, I know it's not that, but I have to keep my job, so I'm gonna appease you. And then root cause, don't suppress symptoms. If you go in and you just randomly change a resistor and all of a sudden things work, but you don't really understand why, you make a batch of 1,000, that problem could come back because you have a tolerancing issue that you fixed the symptoms with. So don't look there unless you have a reason to. This will save you a lot of time. So I've broken this down into 7 basic steps to get you started if you guys haven't debugged before. First thing, don't panic. It's nerve-wracking when you get a board and everybody's looking at you and you power it up and all of a sudden, psst, it's a terrible situation. You feel awful. You feel like you don't know what you're doing. But just take a break, grab a cup of coffee, collect yourself. You got to use your brain to debug. If you're in a frazzle, that's not going to be a good place to be because you're just going to go into shotgun mode and be panicking. Step 2, take this away home with you. If there's anything from this lecture, this is it. You cannot debug what you cannot reproduce. Software guy comes to you and says it's broken. Well, reproduce it for me so I can test it. If they can't reproduce it, then there's no way you can debug it. You're just going to be chasing fairy tales, I guess. Step 3, reconnaissance. Gather data sheets, information, anything that you can about the product, familiarize yourself with it. Step 4, ask the right questions. If for instance, software guy says that he has a problem, you go stand over his desk and you ask him, how do you have it set up? What power supplies do you have connected to it? Did this work before? What has changed? Anything that you can gather information-wise from the observer is going to help you in the long run, because it may have been something that they plugged in a USB device and all of a sudden shorted out or something. Who knows? But they could give you good information, but you want to lead them down that path of asking the right questions. Step 5, this is the most important, observe and take measurements. Play with the device. If you have a device that's exhibiting an anomaly, turn it on, turn it off. Look at everything, listen for things. There might be clues there that'll help you debug something. And then create a theory from your evidence, test it, and then repeat as you break down the problem. Last step is validate your fix, and we'll talk about that at the end. So I broke this down to what I call the Gedanken process, which is, I'm coining after Albert Einstein. It's basically this process where it's just iterative until you get to the solution. And just a quick example. I have a bunch of examples in these slides. I'm going to just skip them, save them for the very end if we have time, but this is one I want to go through. So I have a circuit, very simple, resistor, LED, and a 5-volt supply. These are the things that I've measured and I've observed. So what do these things tell me? I'm going to sit back. I've taken my measurements. Now I'm going to create my theory. The rest of the board is functional, so it's probably not a power issue. I'm not going to look there. Other boards in the lot work. I have 10 other boards that are working. It's probably not a design issue. The LED is dimly lit. Well, the LED is connected. It's passing current somewhat through it. Is it damaged? Maybe. That's something I want to take a look at. The supply that I measured was 5 volts. And I have a low V drop. There's too little current going through the resistor. So looking at this, I already know what's, just from taking those 2 measurements, what could be wrong. Does anybody have a guess? Exactly. Because of the low voltage drop, resistor's probably too high. Maybe it was a misload, or somebody switched it out when they were debugging or something, or the LED could be partially damaged. So I'm going to give you a couple tools so that you guys can co-locate problems. The first important thing, labeling and taking notes. If you have 5 devices, they all look the same. How are you going to be able to tell a difference between them? Have serial numbers or some way that you code them. I always like to, on my prototypes, name them after something like beer or cities. It's just a fun way to kind of keep track of things. And take very good notes. And this last piece, make one change, revert it, and before you try something else. Because you don't know at the end, if you've made all these changes, if it's an aggregate fix. You really want to find that root cause. What's that one thing that's going to change your anomaly or fix it? Tool number 2, statistics and probability. I use this all the time. You can learn a lot from your board population. Is it all the devices? Could be a manufacturing issue. It could be a board design issue. If it's only on some devices, is it a tolerancing issue? Was it a manufacturing issue where they misloaded some components or something was left off? That happens all the time in large builds. Is it just one? It could have been mishandling. Somebody could have had it before and dropped it, maybe broke it. Missing components or missing firmware. Or wrong firmware, sorry. Anomaly occurrence. Does the problem happen every single time? Usually indicative of a component issue or a short. Periodic, 1 out of X tries or something like that. Could be borderline timing issues. You could have, and as it goes down, all these things kind of point to different things to look at. Sorry, I'm trying to go through fast. Tool number 3, getting back to your first principles. Conservation of energy. Never changes. If you do create more energy than you're putting in, you should patent it because you're going to make a lot of money on it. And Ohm's law doesn't change. I don't care what anybody says, it's consistent. Tool number 4, use your senses. Like I was saying, sometimes you can debug something without even taking a measurement by just looking at a board. Things discolor when they heat up. Pads, they'll turn like a blue or they'll tarnish quicker. Feel things. You can feel components getting hot if they're shorted or if they're getting warm. Wiggling cables. If you have crimped cables, it's a huge source of issues, right? If you're having custom cables made. Listen. Inductors that are squealing. That means that they're in saturation. Crackling can be from arcing if you have high voltage circuits. So the smell of warming plastic can be indicative of something warming or cable getting hot. I don't recommend tasting anything though. Oh, this is one of those debug exercises I'll skip through. Measuring, like I said, this is one of the most important things because you can't see electrons, but you can measure their side effects, I guess I would say. I think we all know how to do measurements with voltage, current, resistance, whatnot, but one thing I want to tell you guys that you guys should trust your tools. There's been times where I pulled a DVM out of a bench and the battery was bad or it was old and I was getting bad results. Somebody could have left it in AC couple or your oscope in AC coupling mode, so you're getting wrong results. Why am I not seeing any voltage? Well, it was in AC coupling mode. So make sure that you trust your tools before you start taking measurements. Another thing that you can do is time. If you have a boot sequence where there's LEDs that are toggling, sometimes you can tell where something's locked up in a boot just by looking at the LEDs. A lot of people will just ignore that and be like, well, it just doesn't work. I'm like, well, pay attention. Another debug exercise. All right, technique number 1, A/B testing. We all do this as it is, right? Your remote control is not working, so what do? Swap out the batteries, first thing. You're testing A battery versus B battery. But this isn't just swapping out components. You can swap out PCBs. You can do measurements between A and B. Say you have a working board and a bad board. That's a great place to be because you know what it should look like and what's happening, so it'll help you co-locate a problem where it'll look like wrong voltages, for instance, or LEDs not working. Exercise. Black box testing. This is really good for components that you don't really know what they're doing or IP in an FPGA. Inputting bit patterns and seeing what comes out. I had a situation where I was trying to figure out, I was putting a data bus from an imager through an FPGA and it was outputting data. What I ended up doing was putting in different patterns, A's and 5s, and on the other end I was able to find out that it was flipping the bits. So doing black box testing is not only for FPGAs, but it can work for other things. Toggling power supply voltages, those kind of things, or even resistor values. Heating and cooling. Heat and exacerbates problems. It speeds things up, it causes voltages to fluctuate, and it causes things to be less efficient. This can be a problem if you're making a product that's really hot, but you can use it to your advantage. They have cans of free spray. It's very expensive. You can spray locally on components to cause them to be cooler than others, to see if you have timing issues or tolerancing issues. Or you can use an air dust cannon. If you flip it upside down, you spray it. It's a cheap version of the free spray. Make it worse. I think I use this more in compliance testing than anything else. Because it's really hard sometimes to squash a bug or squash some noise frequency when you're doing compliance testing. But if you make it worse, it won't necessarily solve your problem, but it will show you a causal relationship to what you're chasing. An example of this could be, I have a display, let's say it's an analog display and it's flickering. If I change out to a longer cable and it gets even worse, then it's something with the cable. It may not solve your problem, but it'll at least help you point to where your issues are. Technique 5, this is automating testing. This is for situations where you have really hard to reproduce issues. Say something happens 1 in 10,000 reboots, 1 in 1,000 reboots. You're not going to hire an intern to sit there and reboot something. So it's best to create a way that you can reboot that system over and over again. The challenge here is that you have to be able to capture it meaningfully. If it takes a month to reproduce something and you catch it, but you didn't catch the measurement, you've kind of wasted that opportunity. So this is okay, sorry, the slide was different on my screen. Quick story time. I'm over. No, I'm still good. I was working on a product and we were upgrading the camera's FPGA. It needed to have a larger block count because it had some new algorithms that were running in, and we needed to run it. Same PCB, we replaced the FPGA, had it made. And the same codes were being run. Save the FPGA bit file. It had to be recompiled because it was a larger block size. Camera A, which has the smaller FPGA, which has been a release product, it boots fine, no issues. Camera B that has the larger FPGA, it's a drop-in replacement, pin compatible. It has a rare boot lockup every once in a while. The error report from the boot log says the FPGA is not found. Now, this is an intermittent problem. Sometimes it boots fine, sometimes it doesn't. So I created this system. I used, I don't think they make this anymore, but it was, I remember the website, plc.us. It was cool. It was, had an LCD screen, relays, optos, everything, and then I had three cameras that I've connected to this, and I was rebooting them, monitoring. When the FPGA was loaded, it would toggle an I/O on, so I'd be able to know that the FPGA was loaded to make sure that I got past that point. If you see here, when I caught this, it took 78 cycles to catch it, 12 days, 12 days, 1 hour, and 21 minutes. And that's the only way I was able to catch it. So what was it? The smoking gun was that the FPGA done bit was asserting. Now, if you guys are familiar with FPGAs, they're usually loaded through SPI, so either a SPI flash, we were reloading it through the microcontroller, and then at the end when it's loaded correctly, this is a one-way SPI, it just sends a bit that I've loaded correctly. It's just a single assertion. Well, looking at the boot log, it was saying that the FPGA wasn't there, but when I caught the issue, I was able to probe the done pin, and it had finished. Well, the issue was they hadn't changed the timeout code during boot. They were saying, oh, the FPGA is drawing too much power. You know, that's what they were saying. But really what ended up happening is because the bit file was longer, they had set the timeout to be for the shorter bit file. Longer bit file, it was timing out, and then it would just say that the FPGA wasn't there because the done bit wasn't toggling. That's just a short example of using automation for testing. How do you know you fixed something? When you find the solution, what you need to do is take it away and bring it back. So if it's a replacement of a component, if you're able to replace that component, the problem goes away, take the old component, put it back. That's a good way to verify that you fixed the issue. Do it multiple times if you want more confidence. And the explanation will make sense. It won't be something along the lines like, I don't know why this makes sense, but I changed out the capacitor and all my problems went away. Usually that's going to lead to further problems down the way if you don't have a good reason for it. And then further testing and using environmental testing. If you have an environmental chamber, it's really good to ramp things in temperature, high, low. It'll exacerbate issues. Here's my contact info, but if you guys are up for it, I can run through the examples if you guys want to stay, and we can do some exercises. Sorry, I feel like I've been talking a mile a minute. I get nervous and I talk fast. Okay, so we went through this one. Okay, simple. Power applied, no LEDs turn on. Any guesses? Are they connected? It's connected. You applied power. Power supplies on, saying that you have whatever, 5 volts, zero current. It's a good one, but no, it's not that one. That's a good one. It's more simple than that. No power because of the connector was cold soldered. You guys know what cold solder is? There's a short, or the processor was not programmed. That one killed me. Power's applied. Power LED turns on fast and fades off slowly, and this consistently repeats. That's right. The discharge is capacitance. It's the power supply is discharging. Input from the power supply is faulting and restarting. The fading from the power supply is the bulk capacitance. So turns on really fast, you have a fault, and then as the power supplies typically have a lot of capacitance to them, it will slowly drain out. So what you're seeing is that it's trying to restart. So this is one of those examples. By just watching the LEDs, you can figure out what's going on. So voltage can tell you a lot, but I like to look at current. I think it can tell you a lot more than voltage. Usually voltage stays constant because you're working on, except for LEDs, those are current devices. But it's good to be able to compare for a working board and a non-working board to see where something's at state-wise. The working board has 20 milliamps, then it goes to 1 amp, and then 1.2 amps. This is typically like a boot cycle where it generally ramps up, so power supply stabilization, loading code, and then when it's in idle. On my nominal board, I have 20 milliamps, then it goes to 5 amps, and it repeats. That's correct. The internal power supply is going to overcurrent protection, and hopefully you've built in current protection for your device. And most of the time, these devices have either they overheat, they'll shut down, and they'll try after a certain amount of times. So that's exactly what's happening with this one. Good guess, or good answer. Working board, 20 milliamps, oh sorry, anomalous board, 20 milliamps steady. So we know we have power to the board, it is sipping current, but it's sitting at 20 milliamps. What can... Close, very close. Anybody else? Sorry? Could be. Sorry? That's a good guess, but this scenario was that the reset was being held low. And you can tell that because it's in its early state, right? A/B testing. You guys see this? This one's easy. Obviously, where's the change here? This display became functional when I swapped the display. Wait. I might have messed this up. Did I? This one? Yes, this one. Sorry, it's kind of hard to read from that angle. So this is just a quick A/B sample swap. Black box testing. Like I was saying earlier, I've done this before for testing. Even like buses that you're unfamiliar with. I mean, are they big Indian or little Indian? You have no idea sometimes. Just test it and find out. So what I would be doing is putting AAA in, and I'd be getting 5 out. 1 in, and I'd be getting 8 out. Anybody know? That's correct. Swap of the bit orders. In this case, the FPGA was sending out the LSB first. Is that it? I think that's it. Well, here's my contact info. Yes.
Are you getting more frequency issues? So, for example, like that we're seeing more, cameras is
Am I getting more frequent?
like issues that you're coming across.
Oh, now? I think.
Because in the past, like I've always dealt with like power issues or road issues, but like now more and more, people smarter than me are talking about
If you're talking about wireless, I have some experience with wireless, but if I were going to talk about frequency issues, it'd be more along the lines of signal noise. As you increase in speed with your communication, you start to get into higher bands where you start having reflections. You start having just strange behavior that you learned in college, but you didn't think you'd ever see. I actually had a reflection issue, which was really, really strange. My previous employment, and what they ended up doing is on the I2C, this is MDIO because we were doing Ethernet devices, but the company that we contracted out to do the layout took the bus and they split it on the board, which you're not supposed to do. You're supposed to have everything serially. So there was one component that we were watching, and I asked the software guy. He had a command line interface, and I was like, just read the ID of the chip, and you could just see the ID changing every time that we were reading it. So we get in there, and you have to be careful when you're measuring reflections. You either have to use a FET probe, because when you use like one of your passive probes, it'll affect the circuit. You're adding capacitance to it. And there's some things you can't measure without a very expensive scope, like PCI Express. Like it's difficult. But yes, I've been, more of the problems that I've been running into lately are thermal issues. Things are getting smaller. You get higher leakage with smaller transistors, so you have to be careful with your thermals. And as I've gotten progressed into further on in design, definitely the higher frequency cause issues. And they're doing different things like for power. Can I keep going? Okay, cool. I had this board that I made. It had a microprocessor on it. Well, it was a TI processor. And what they've been starting to introduce is something called AVS, automatic voltage scaling. And what they'll do is they'll profile these chips in the factory, and they'll program some OTP in there for set voltage ranges that they'll function. The lower the voltage that you can get, the lower the drop is. But because of transistor variability, it could be like 0.8, it could be 0.85, it could be 1.0. It's different for each chip. But what I was seeing with using this AVS is it worked at 750 megahertz, it worked at 1 gigahertz, but 1.2 megahertz or gigahertz, we're starting to have issues at temperature. And what we're having was that the AVS scaling was off, and I was getting thermal runaway. As a processor gets hotter, the leakage current gets worse, and it can asymptotically shoot off and current draw and get even hotter. It's kind of like a closed loop unstable system, I guess. Did I answer your question?
Yes, thank you very much. Because especially with communication devices that have like smartphones, we're adding more and more antennas. It's NFC,
Yeah, absolutely. Yes.
And so we're seeing more frequency loss.
Yes. Yes. Are you talking about any product in specific? No. Nothing you can talk about? Yeah. The wireless thing's crazy. Not on your product. Because you're in one sense, if you're making a PCB, what you're trying to do is avoid wireless signals, and when you're doing a wireless signal, you want to exacerbate that issue as much as possible. And keeping things further away, shielding things. I see a lot of caps, like they put metal caps on parts to try to prevent things. Sometimes you got to increase pull-up strength because you get crosstalk. And I was actually interviewing for a phone company, and I had an interview question about how would you fix an issue we have a I2C or I2S bus, and we have pull-ups on it. We need to reduce the pull-ups on it to save power. But we're having wireless signal integrity issues. How would you go about fixing that? Well, you have a number of ways that you could go about it. Obviously, like bury traces, move them further away, those kind of things, increase your drive strength. There's a number of things that you could try to do. But yes, it's getting, as the boards get bigger and more complicated. The most complicated board that I ever worked on was an 18 by 18 inch networking board that had 52 SFP ports on it, and it was 48 layers. I mean, this thing was thick. I wanted to take it out in the woods and try to shoot it because it looked like a bulletproof plate or something. It was crazy. The boards themselves were like $2,000 a piece. But the amount of issues that you have when you have components that are co-located and interacting, that's a very good, a very hard problem to solve sometimes. But a good way to do that is just turn something off. See if your problem goes away, right? Isolate the issue. Simplify things.
Do you have a favorite non-standard debugging tool? It's not a multimeter, not an oscilloscope, but
My finger. You can induce capacitance with your finger. So I've been able to find borderline issues by just running my finger over a trace and causing bit errors. Checking things warm. That's one of the things I'll start it up and I'll start touching the processor, see if it gets warm. You got to be careful with that because you can burn yourself. If that is a non-standard, non-calibrated tool, but unfortunately I can't sell it. But yeah, that's yes.
Similar vein, how often do you employ your capacity
On my finger? Oh. That sometimes when I lose my patience, yeah, that's a good way to do it. Yeah, just hitting it. But sometimes if you're ever working on something very expensive, you don't want to do that. Let me say that comes out of your paycheck, right?
How do you deal with bugs that only show up when deployed in a new environment? Lots of things change. So I have things like work in the lab, and then I move into a new environment. I don't have that control to compare to. Well, I was working in the lab, and the hardware has changed, the software has changed.
So environmental differences. I would ask you, what can you bring from your lab with you into the new environment? Is there anything that you can reproduce or slowly change to try to find what the issue is? I mean, is it a big device?
Yeah.
Fairly big. Well, sometimes you can, pull your power supply out there. Try to isolate things in the room. Is it temperature? Can you cool it down? Try it in the morning. Try it in the evening. Try to create a theory and then find a way to test it. Sometimes you got to do crazy stuff like testing an encoder, right? I'm hooking it up to my turntable to measure it, to make sure that the pulses are good, consistent. So sometimes you got to think out of the box and do some crazy stuff. You're done? All right, I want to take a selfie real quick. A lot more people showed up than I thought, and I really appreciate it.